Welcome to a lesson with Dr. Powell. Let's take a look at a way that we can take the derivative of the inverse function of a function, and we're going to do that implicitly in some kind of way, where our final result is actually going to be expressible not in terms of x, but in terms of y, like in terms of the actual function we're taking the derivative of. I mean, if the function was g, say, we're finding the derivative dg dx as a function of g, where you see g is the variable instead of x. And why is that so, and how do we do it, and what for? Let's dive in and see. So we'll start with the function. I just wrote a function out here. This function does have an inverse, and it is computable. The viewer is encouraged to actually find the actual inverse function and plug it in at the end and see if the two are equivalent in what we're doing. So for starters, okay, we can let f of x just be y. Okay, y is equal to the natural log of something minus 1, and we take a derivative. Now I'm going to use differential symbols here, dy and dx. I think of dy and dx as being rise and run on the tangent line to the curve. So I don't think of them as being delta y and delta x, but they are exactly rise and run on the tangent line at a point. So I can think of them like this. Now, assuming that dx is non-zero and dy is non-zero, then we can actually, flipping this is fine, or doing kind of any operations with dx and dy as being rise and run on the tangent line in relation to each other, using that assumption of being away from zero, we get all kinds of relationships with derivatives. And the exceptional case when you get zeros are usually fillable, like with hole filling with limits and stuff in continuity. So really we can see a lot of relationships just by playing with these symbols, and it's mathematically rigorous and sound with a few technicalities worked out. All right, so if we have dy over dx, right, that's the derivative, and we end up getting this, what did we do? We used the rule, the derivative natural log is 1 over the input, then we multiply by the derivative of the input. Notice we use the chain rule again here. The inside is negative x plus 1 in the e function. Derivative of e is e to the something, but then you multiply by the negative of the derivative of the inside. So chain rule a couple times, and we have the derivative. Great. Now, usually when we find the inverse function, what do? We swap our x's and y's. Why? Well, usually the y value represents the output of a function when we're working with x's and y's, and the x represents the input. So that's just standard there. So we switch x's and y's, and now when we do so, the y that we see is actually the output of the function we're now considering, the inverse function. So after swapping x's and y's, y is going to be the inverse function. All right, and x is going to now represent input. So, but we also notice that when we swap x's and y's, we have dx over dy. Okay, and that's equal to this. But if we want the derivative of f inverse, or y, say in this case now, because now they've swapped, we reciprocate. So take a reciprocal of this fraction dy over dx, and that'll be the derivative of the inverse function. But notice it's all expressible with y's now, which is what we were aiming for. Now, if we wanted to represent in terms of x, what would we do? Well, we just plug in for y what it is in terms of x as the inverse function, and then we can proceed and go like that. So if the viewer wants paused the video or done it on their own up to this point, or you can pause it right now and find the inverse function. That's great. And then let's check to see if it really does work. So what is the inverse function here? Okay, well, let's take a look. How would we do that? Well, in this case, you know, we can take that, swap our x's and y's and solve for y. So in swapping, we would have x is equal to the natural log of e to the negative y plus 1. That's a plus 1. And then plus 2 minus 1. All right. Now, okay, we can add the 1 over, so we have x plus 1 is equal to this, raise both sides, put both sides as exponents over e, and we do that so that the e and the natural log will cancel because we put they're inverse operations of each other and they cancel out. So we end up getting e to the x plus 1 is equal to e to the negative y plus 1 plus 2. And then what do? Then you can subtract the 2 over, so we get ex plus 1 minus 2, and then that's equal to e to the negative y plus 1. We can natural log both sides. Natural log after the 2 is moved over here, and then on this the ln and e will cancel out, and you'll be left with negative y plus 1 over here. Okay, so little swapping can move this natural log over here to make it negative, this negative y over here to make it positive, and then the 1 will stay over there. So it'll look like y is equal to negative natural log of e to the x plus 1 minus 2, and let's see, yeah, okay, and then plus 1. All right. Now, if I go ahead and plop this now, because this, well, now this y, because it happened after switching, is actually this right here. So this is actually the inverse function. I could take a derivative of this. Whatever I get as a derivative of this should match this right here when I plug this, it in, this as f inverse of x in right here. So if I would take a derivative at this point, let's just see what that is. That would be, okay, so taking a derivative here, that would be what? Negative 1 over e to the x plus 1 minus 2, that's an x, and then we, of course, multiply by the derivative of the inside, which is e to the x plus 1. Derivative of x plus 1 is just 1, so chain rule, multiply by 1, it's fine, just that's what we get. So, wait a minute, is this going to be the same as this over here? Okay, that's the question. So we could take this, let's see, we take this right here. If we plug this in for f inverse of x, will we get that? Let's see what happens. So if we have e to the this plugged in. Now notice that when I plug this in right up here for f inverse of x, I'm going to get negative of all of this. So I'm going to have a negative 1. That'll cancel with that positive 1. So the ones you can kind of ignore. So then right here at this point, we have, okay, so we have negative natural log e to the x plus 1 minus 2. That's going to become a positive with this negative, okay, negative, negative, and then we'll end up having the natural log of, okay, so positive natural log, and that'll cancel with that e. So e to the positive of that cancel with the natural log, and you'll just be left with e to the x plus 1 minus 2 right here, and that minus 2 will cancel with that 2. You'll be left with e to the x plus, oh, it's right here, e to the x plus 1 on the top. Wow, that really is kind of working out a little bit here, isn't it? Okay, so what about the bottom? All right, taking a look at the bottom now, what's going to happen? When we plug in, okay, so when we plug in this right here into the bottom, again, we're going to have something very similar. The ones will cancel out. Okay, so because, yeah, it's actually the same calculation here, right? and then we have e. In fact, we'll end up just getting cancellation. Well, pretty much it takes us to the inside here, e to the x plus 2 minus 2. So yeah, so e to the x minus 2, is that right? Yes, e to the x plus 1 minus 2. This is what we're after right here. Let's see if, yeah, actually that's exactly right. We get that because we don't have anything else we're adding on. That's just in the exponent. So it's just that, and that negative is right there. It checks out. A little, you could have fast forwarded my little explanation there or maybe done it on your own, and if you can see the cursor moving up and down, but nonetheless, it does check out, and you're encouraged to work through those details to see that just in verification. All right, let's look at one more example here before we're through. All right, let's take a look at y is equal to the secant of x. We're going to determine the derivative of the inverse function of secant. Now, of course, this is secant restricted that we're taking inverse of, because secant is a periodic function, does not pass the horizontal line test, does not have an inverse. Secant does not have an inverse unless it is restricted in its domain. And the way it's, and its restriction in its domain is actually from 0 to pi. And if you look at the graph of, secant as you go from as you go from 0 to pi, let's see, it looks something like this, and then something like that, okay, roughly. And in taking a look at that, okay, so from 0 to pi, that's going to be, past the horizontal line test, it'll have an inverse. So that's kind of where we're working. All right, and going forward, we go through the same steps as last time. We simply just take it. So the first step 1, take a derivative, dy dx, of secant. Step 2, swap your x's and y's. So now it'll look like dx over dy is equal to something with y's over here, where now y represents the inverse function. Okay, then swap, or not swap, but take a reciprocal. So the last step was swapping x and y. This step is taking a reciprocal. So we get dy over dx. Hey, that's going to be the derivative of the inverse secant function. So, and that's just this, but it's expressible in y. All right. Now we know what y is. It's this, so we can plug that in here. And this is what it is in terms of x. I would like to write this, though, in terms that are not trig functions. I don't want trig functions in here. In fact, think about what this is. Secant inverse outputs an angle, and if you evaluate a trig function at an angle, you have a ratio or something. You don't have a trig function anymore. You've already passed through it. Similar over here. So let's see what we can get. Remember, secant inverse of x is an angle. And it's an angle between 0 and pi. So the output of secant inverse has the goes from 0 to pi, and the input of secant restricted goes to 0 to pi. Notice how those swap places. Output and inputs have swapped. So now one little comment here. From 0 to pi, either we're in this quadrant or this quadrant. In this quadrant, secant and tangent are both positive. In this one, they're both negative. So for multiplying the two together, we should always get something positive. Negative times negative is positive, positive times positive is positive. So that kind of helps us with our signs as we go in trying to figure things out, particularly when we're taking a square root and we have a plus or minus. So let's take a look and see how we're going to do this. We look at a triangle. Now there's a few basic triangles that we can consider every time we think about our angles. Here's one of them. So if we have an angle theta, this side length we call 1, tangent theta, and secant theta. This is kind of the format that we're going to use, all right, for our triangle. But what's our angle? Theta, in this case, is secant inverse of x. So we replace theta with that in both cases, and this guy is really easy to compute. This is secant of secant inverse of x. Of course, secant inverse of x outputs between 0 and pi, so really you can pretend that secant is secant restricted because what's going into it is part of that restriction. They're inverse functions of each other. They cancel each other out, and we end up getting x over here. Okay, so with this Pythagorean theorem, we have x here, we have 1, and we have this length. Now, if we want to figure out what tangent of secant inverse of x is, we can use Pythagorean theorem here, or just realize Pythagorean theorem extends as we go all the way around the unit circle. That's really what, well, I guess it's not a unit circle in this case, but because the hypotenuse isn't 1. But nonetheless, everything rescales or scales up and down. So we can take a look at that way, and we can compute what the tangent is using the Pythagorean theorem. 1 squared plus this squared is equal to x squared. 1 squared plus tangent of this of secant inverse squared is equal to x squared, using so we can kind of think x squared minus 1 on one side is equal to tangent squared, and then square root. There's going to be a plus or minus square root. Which one to pick? Well, in our calculation, we have to have this whole thing being positive. This works right here if we just put an absolute value of x on right here. So this right here is the derivative of the inverse secant, and we can do it relatively without too much trouble if we just kind of think like this. I like these differentials, you know, and kind of visualizing what happens with well, swapping your x's and y's and then reciprocating right here, and you express your derivative completely in terms of y. Remember what y is after we make the swap. It's the inverse function. Think of this as an angle that you're plugging into trig functions, evaluated on a right triangle, and the thinking about Pythagorean theorem, and voila, absolute value just comes from this fact that we wanted secant times tangent always be positive in this particular case. Thanks for watching.